Yeah, 74. You want 74? 74? 74 is A. And 75? Brandon?
The box with elements on the periodic table is shown, which is the atomic number, D.
75 is D. 73 was C. 76? Brandon?
The box for an element from the periodic table is shown, which is the atomic mass, A.
A is correct. 77. Mari?
Why did J.J. Thomson use that? It must be parts of all of the atoms of all elements.
A is correct. Your DNA? Yeah, the gamma is. So we're talking about the alpha particle. Elijah just read about the alpha particle. And they're not emitted by elements smaller than lead, right? So what was uranium named after?
Uranus.
Yeah, actually it was named after Uranus. The planet. Shh. It's a good chemistry joke. Now, Uranus was discovered in 1781. So when was uranium discovered?
1860s.
No, 1789. So Uranus had to be discovered first, right? It was named after it. I know. I just see if you're following along. It's kind of funny. So about 8 years later, uranium was discovered, and they named it after Uranus. Now, what's the significance of uranium? No. Uranium has huge significance to us as far as the age of the Earth. Uranium was used to date the Earth by a gentleman by the name of Claire Patterson. Okay, so what he did, he noticed that there were 3 different types of uranium. Uranium-204, uranium-206, and uranium-207. And he noticed that one was stable and the other 2 moved around a little bit. And that does not have any stable isotopes. You can see here that stable is not listed. Only the half-lives are listed. The half-life is basically the time it's going to take for half of it to change into something else. We'll do a lab on half-life. Probably when you get back, like I said, we're going to the lab tomorrow. And the isotopes of lead. So lead comes right before bismuth, and you can see here that it has 4 stable isotopes. And what does stable mean? Raise your hand. What does stable mean? Right, it does not have a predictable half-life or death. Now, something can cause it to change, but it's just not predictable. A half-life is giving you a predictable, you flip a coin, it's 50-50. Either you're going to change or you're not going to change. And if you keep flipping that coin, eventually it's going to change. But something is stable, it doesn't have that probability.
Or E negative, they have 1 negative charge. Their mass is so small compared with the mass of nuclei involved in a nuclear reactions that it can be approximated to 0. Beta radiation consists of a stream of fast-moving electrons. An example of the beta decay process is the decay of iodine-131 into xenon-131 by beta particle emission, as shown in figure 24.4. Note that the mass number of the product nucleus is the same as that of the original nucleus. They are both 131, but its atomic number has increased by 1, 54 instead of 53. This change in atomic number occurs because a neutron is converted into a proton, as shown in the following equation.
Okay, so have you seen this equation before? Raise your hand. Have you seen this equation before? On page 863, the equation where Sam just finished reading. N yields P plus beta particle. Never seen that before? Raise your hand if you think you've never seen that before. So you didn't draw the little Pac-Man and the little particle equals the neutron. In your notes, you had a proton plus an electron equals the neutron, right? this is the same thing. Neutron yields the proton plus the electron. So we're just reinforcing that. I know they've written it a different way, but you need to understand that that's what it is. It's just the proton yields, or the neutron yields the proton plus the beta particle. Now we want to, in your notes, write this reaction here, because this is an example of the beta particle that's a product from iodine. So iodine is producing a beta particle.
Hey.
60 is B.
Wait,
61. Florentina?
61 is, which is the number of protons, and 36, 26, iron, and that is C.
C is correct. And 62? Eugene?
It says what's the correct symbol for the atom? It's B.
And 64? Let's go with,
We skipped 63.
oh, correction. 62 is B. 63, go with Riley. Or, correction, Mackenzie. You moved seats on me. Sorry.
Which?
We're on 63. Oh, that would be 13. Shh. B is correct. Riding on a motorcycle, and he was just going in and out of traffic really fast, making those curves, like you see right here. So it's really small, whereas like a semi, a tractor trailer, if it tries to do that, it's going to flip over. So it's not capable of having a greater slope. So you can see here this slope is greater than this slope. Is the reason why alpha particles are helpful. Because when you get really big, like if you're uranium or radium, you're going to need to lose some of that weight, these other isotopes that are radioactive, to become more stable. Now, on the periodic table, you'll notice that lead is the last element that has stable isotopes. Lead right here. Everything past lead does not have stable isotopes. What does that mean?
That everybody afterwards has radiation.
Has a predictable death. When we say half-life, it's like flipping a coin. You got a 50% chance you're going to stay, 50% chance you're going to die. So they have predictable deaths. After lead, all the elements have predictable deaths. Okay? Now, when you get to polonium, it only has one particular typical isotope, because you see it in parentheses here. Now, uranium has more than one. You'll see it has 238.03. But when you see the parentheses, it tends to only have one isotope. It varies a little bit because you would think the pattern would be consistent all the way to the end of the periodic table, but it's not. Does everybody see that? So parentheses, one type isotope. Now, bismuth is the first element past lead that does not have a stable isotope. So you're starting to see then this change of one element into another after lead. We're looking at these decay processes. You have a known and you have an unknown. For example, living, you're taking in carbon-14, that's the known. The unknown is the dead, how much carbon-14 is there. So you have to do an investigation to find that out. Then you look at how long it takes the carbon-14 to change into nitrogen. That's how you figure out the death. Is everybody clear?
Yes.
This works for every single thing you're trying to date. You have a known and unknown. So Claire Patterson, he's using uranium. Which uranium is he aging the Earth with?
Because of their mass and charge, alpha particles are relatively slow moving compared with other types of radiation. This alpha particle.
Daniel. Claire Patterson?
Can I answer?
Claire Patterson. Do you know who Claire Patterson is?
Scientist?
Yes. He was a scientist who dated the age of the Earth. Now, was he a European, a Frenchman? Or was he a Mexican? or was he a Canadian? Raise your hand. Daniel?
Sounds French.
French? Canadian? So raise your hand if you think he was Canadian. Alright. Raise your hand if you think he was French. I don't know, you Frenchman? Or raise your hand if you think he was Mexican. Raise your hand if you don't know. He was American. He was an American. I say that because you ought to know some famous Americans. I mean, he dated the age of the Earth. Right? It's pretty important. From Caltech, Claire Patterson chose to use 2 uranium isotopes. And specifically, he chose uranium-238 decays very slowly into lead-206, while uranium-235 decays less slowly into lead-207. Both rates are well known, so measuring the ratios of lead atoms to uranium ones shows how much uranium has disappeared and allows the sample's age to be calculated. So in this scenario, what is the known? What's the known? Anybody know? I didn't tell you the known. That's good. You don't know. I didn't tell you the known. The known that he used would be meteorites. So he went all over the Earth, and he found meteorites. And he's looking in the meteorite for what element? Lead. Because he needs to know how much lead is in the meteorite. And that's going to tell him the known. That is the period of time from when it was out in space, and now because it's still in the meteorite, how much uranium was there. Because uranium has a set pattern that it follows. These two produce a ratio that he's looking for. Is everybody clear? That's what the known was. Now you can read the article and study a little bit more if you want, but he had to have a known, which is the meteorite. Then his unknown is the Earth. So he had to go through the Earth and find, a contaminated free area to find his unknown and then establish the age of the Earth based on that. But he used the meteorite. That's very important to write down. He used the meteorite to establish the known. In this particular scenario, Claire Patterson did. Now, in this situation, the bell work does not produce, I guess you would say, 0 acceleration. You've got an acceleration of 0.20. So our normal force upward is 100, and our gravitational force is 98. So we don't have a net force of 0. Does everybody see that?
Yeah.
Right. So we have a difference. Yesterday we learned about the net force of 0. Now we're learning about, you can use this information to calculate a value, which is important. That would be an acceleration.
I love my tablet while
You can go get it.
So does that
Now,
mean that if you were to like show an example of that like on a table or something, it would like fall through the table? Because he was saying how it's like added to the same position when it's 0, like when the forces cancel out. But if they don't cancel out, would it push through the table or something like that, or what would actually happen?
the table could collapse, yeah, if it was heavier. But in this situation, remember, you were lifting this off the ground because the normal force is greater than the gravitational force. Now, on the back side, we do have some examples from the homework, and I will try to go over those at the end of the period, because today we're doing a similar thing that we've done before, that is, we were testing for acceleration. Now, if you have a rapid change in velocity, what do you have? A high what? You have a high acceleration, right? Rapid change in velocity. If you have a slow change in velocity, you have a slow acceleration. Does everybody understand that? Okay, so you can do that with the ticker takers, but we're introducing this new equipment up here, and that's really what's new, is using equipment you've never used before to try to calculate these changes in velocity, because the balls are going to be going down this little ramp, okay? So you're going to test that.
So we're doing a lab today?
Yeah. Now, the last topic in this chapter is concerns friction. So the next lab, we'll actually do probably 2 or 3 labs on friction. There's like a force associated with friction in Newton's laws. And that'll be the last major topic, then we'll move out of this lab. Correction, out of this chapter. The last major topic would be friction. Is everybody clear? So let's do this very simple lab, see if you can use this equipment up here, and we'll collect some data.
Yes, it's on.
It's recording. I'm taking shots.
So what was your time?
The time was 1.2 seconds.
And what was your velocity?
The velocity, it says 10 meters per second.
It looks like the velocity here was 1.26 meters per second.
Oh, okay.
Yeah.
So you should be able to pull out that data over here. It looks like you've got
Wait, somebody called.
your velocity here of like
Nobody called
1.3.
Yeah.
Looks like it's close to. Why is it negative?
Because it's going down.
Yeah, it's going down. Very good. Yes. Now, when you do the graph, you can move the graph, and it'll give you the actual value.
type
So,
ball.
if you,
still have our lab.
I do.
Can't do it.
If you go to the graph part, you can move or and so forth. Excellent. Really good. That's good.